So this is lecture 4, and lecture 4 discusses these 3 bullet points. The first one is to modify the processor clock, and very soon I'll discuss why I have to change the processor clock from the default and what value I want to set. All this we will discuss later. And the second bullet point is to define traits for the clock sources and then implement the same trait for a few or more than one FE310 clock sources. And if you are not familiar with the Rust trait, no problem, very soon we will see with an example how to define a trait and implement them for an instance. Okay, and the third one is which this lecture covers is defining the PWM traits or pulse width modulation traits, and then implement them for the FE310 PWM instance 0. So why all these three are coupled together in the lecture 4 is there's a need for me to change the processor clock, but then to verify if the processor is actually running in the clock which I said, I need a way to probe it with my oscilloscope, but that is most of the processor the debug board won't have a pinout from the actual processor clock itself. So most common way to verify that is you use that to drive the PWM, and mostly the PWMs are even in FE310 it's multiplexed to the GPIO pin, so that means it should be available on the breakout board as a probable pin. You can probe it. So with my oscilloscope I should be able to read the frequency of the PWM output, and from the PWM configuration I can infer what the actual processor clock is. Okay, that's why all the three are grouped together in this lecture. Let's jump into the first bullet point. Why should I change the clock frequency, or why do I want to change the clock speed in the FE310? So first, this is the default clock speed. So at boot up, the default speed of the clock is 16 megahertz. So if you do not make any change, and if you have a Hi-Fi 127B board, then your processor would come up at this speed. Okay, so now why do I want to change this? That is because if you go to the FE310 manual and for UART baud rate, so the clock speed has a direct relation with the UART baud rate. Okay, and I want to run the UART at 115200. That's the target baud rate I want to run all through. First of my experiments or anything, I want to fix this board as a 115200. Now 115200 can be achieved at many clock speeds. So all you need to do is that it should be a device register, and whatever the value you feed in, so input frequency divided by that would be your actual baud rate. That's why if you see here, so if the clock is 16 megahertz, and if I want to achieve 115200 baud or baud rate, then the actual baud I see 115207, but I'm not clear because if the divisor value is 139, then this should be 139 plus 1, which is 140, and the value should be 1142 something, which gives more error percentage. So I'm not sure. I did not reach to Sci-Fi to check with them, but instead but one thing I observed when I run at this clock, when I with this processor, with the default processor clock at 16 megahertz, and when I tried to run UART at this baud rate, there are a lot of errors. So the receiver is not able to grab the characters properly. So that's why I want to change the processor clock to 200 megahertz. That would reduce the error percentage 1, and also that it would give, since higher the clock speed, more things I can run. That's another reason. But I do not want to go too high as well. But that's why there isn't any other reason. But this is the main. I want to reduce the error rate, and why I couldn't choose 31250 or this target baud rate where the error percentage is 0. So the serial tools which I have with my Mac Mini, it doesn't allow me to, or it does not support these baud rate. So the one common baud rate that is supported by both FE310 and the serial tools on my Mac is just 115200. That's why I have to stick to this 115200. Okay, so that's the reason I want to change. And the new clock frequency, what I want is 200 megahertz, and I want to run it as 115200 baud. Okay. So now going back to this clock settings, and so this is the default, and how do I change this? What should I do to get this 200 megahertz, right? So first, without PLL, you cannot achieve this 200 megahertz. So that's why first disable this PLL bypass in the default. That means that bring PLL into picture, and then feed the PLL with the 16 megahertz crystal oscillator, and then configure this PLL so that so PLL has a three operators here. So first divide the input reference, and then at the first stage output, then you have a multiplication factor by which you can multiply the first stage output, and then there's a division factor at the end to divide before PLL gives the output. Okay, so these are all the three stages inside the PLL. So with the 16 megahertz into the PLL at the first stage, divides that by 2, that would become 8, and the second stage multiplies that by 50, that would become 400 megahertz. And in the third stage, if it's divided by 2, that would fetch me 200 megahertz output. Okay, so that would be the one at the output of PLL out. And then I have to just select PLL select here. Then that's the one that would be fed into all these three clocks. Okay, now let's get into the code. And if you see the directory structure here, this is slightly different from the one in the previous lecture. That's because I removed the driver package and added the traits package and added FE310. So what is there in the traits? I have created a PWM trait and a clock trait for the clock sources. So in Rust, a trait is nothing but a group of methods. Okay, in simplest way, that's the easiest way. The easiest way to define a trait is as a group of methods, and that's what how do you define that? So trait, and you give a name, and define a set of methods, just the signatures, and the implementation don't have to be here, and it wouldn't be here. We will see where it is implemented. So what this does is, this defines this what it mentions is a clock source would have these 5 characteristics or these 5 methods. Okay, so now in FE310 there are many clock sources. For example, you have a crystal oscillator, high frequency ring oscillator, and low frequency oscillator, and a lot. Now to implement, so what this trait does is it abstracts. Okay, so this provides a very good abstraction layer. So any clock source, it can be enforced that any clock source which a platform should support should implement these 5 traits. That means that the portability will be good, and its readability is good, and the maintainability is good. That's how. That's why this traits are very powerful in Rust. Okay, so now for us it's enough for now. So now let's see how I have implemented this clock source trait. Clock source trait for high frequency crystal oscillator. So as I mentioned, in FE310 there are many clock sources. So one of that is the high frequency crystal oscillator. Okay, and I have defined a structure, high frequency crystal oscillator, and with 2 items. One is 2 elements. One is the frequency, and the other one is the status. And I have implemented a method new to get create the instance of this crystal oscillator first. And when the method new is called, the default frequency would be set to 16 megahertz. And would that be enabled? it's not enabled. So that's why the default is set as false. But why this frequency has been set as 16 megahertz? Because it's a crystal oscillator, and it can't be changed. However, for ring oscillator you can change, but this is crystal. That's why. But when I implement the, now you see here, this is the implementation part of the clock source trait for this particular instance of high frequency crystal oscillator clock source. Okay, so this is how you implement the trait for the clock source, and the actual implementation is here. If you see here, you have those signatures here, but this actual implementation for high frequency crystal oscillator is here. So the actual implementation is separated from those abstraction layer. That's the another benefit of this one. Okay, so get frequency, since it's an crystal oscillator, it's just gonna return whatever the frequency it is there. And to set, if the value is 16 megahertz, that's the only thing it's gonna allow that to assert. Otherwise, it's gonna, what is that? Panic. And to enable, so I have defined this register address here based on the manual. So high frequency crystal oscillator config is offset 0x04 from the PRCI block. So in the memory map, the PRCI starts with 0x1 followed by 3 zeros, and then 8 followed by 3 zeros. That means with an offset of 4. So this would be the address for high frequency crystal oscillator. Okay, and to enable that, so this is the register details. So 30th bit should be set to 1, and if it is, because it takes some time for the oscillator to be ready, you can probe this, you can wait on this bit 31 to check if this is ready or not. Okay, so that's why to enable, 1 left shifted by 30 and or with the value. So most of the registers, it's a better practice instead of just without writing some value into that, because if you do that, you might overwrite the other bits. However, when you do like this, so read the actual value there, and then just modify the bit number 1 alone, sorry, bit 30 alone here. So or with that, so that means that the 30th bit would be set. That means it would enable, and wait for the oscillator to be ready. So the 31st bit, so read and with the 31st, or the 1 at the 31st bit, and if the AND operation is true, that means that it is ready. Okay, so that's the enable, and disable is the other way around, where you set that bit to 0 and AND, so that when you write back, that bit would become 0, so it gets disabled. Okay, is enabled is, we have a flag here. Whenever it's enabled, we set it to true. Whenever disabled, we set it to false, and so on. Okay, so this is the actual implementation of the clock trait, and here I have mixed the methods on struct and the traits on the same struct. You can see here, so there's only one high frequency oscillator structure, and I have implemented a new method with that, and I have also implemented the traits for that. Okay, and now the other advantage of this trait is that now this thing to keep in mind when you define a trait is that it should be generic enough to accommodate all the clock sources. Though this crystal oscillator doesn't support set frequency, I can't. It's better to have this because some other clock source might need it. So that's why when you define the traits, you better consider common. That's why these traits are group of methods which can be considered common across or common behavior across all those structures. Okay, the second one, so now we have defined the traits for the clock source and implemented for the crystal oscillator, and then we have to feed this crystal oscillator output to the PLL, and you have to configure the PLL, and that's what is this code is all about in the FE310 clock.rs. So mostly once you set the clock and the runtime, where it's very rare to change the clock very frequently. That's why I just created one method here for PLL to configure. So first read the value of the PLL config, and I'm not I'm not enabling the PLL right away. I'm just modifying in the local variable here with all those bit values here. So first select the PLL out, PLL reference, select to high frequency crystal oscillator, bit number 17. Let me grab the so this is the PLL config, and you have the R value, F value, Q value, and a reference select bypass. And once the PLL is locked and ready, then this bit will be set. So first, this is what. So set the reference to 16 megahertz clock and disable the bypass. Set the R value to 2 so that the input is divided by 2 at the very first stage, and times 50 the second stage, and divide by 2 at the last stage to get 200 megahertz. So all these values bits are modified in the local variable into this val variable, and then it's written into the register address. So as a volatile write into this register address, this particular value is written into that here. Okay, then it wait for the PLL to lock and get ready. Okay, that's it. So that's all about the clocks. Now let's jump into the PWM trades. So PWM, I have slightly deviated from the common methods what you might see. So most commonly you will see a prescaler and a set frequency and set duty cycle, and then you have an enable and disable. But here, however, I have defined the trait with these methods. One is prescaler, which is to divide even before feeding into the PWM. What should be the division factor that should be used to divide the processor clock. Okay, so 200 megahertz, and if the prescaler is set as 2, then the input to the PWM itself will become at 100. So whatever the frequency is fed in, this prescaler value would just scale before it's fed into the PWM. That's what this prescale is. And to set the frequency, I have defined this trait. So now let's see how this is implemented for FE310 PWM. So in FE310 there are 4, I think more than one instance of PWM. However, I'm using PWM 0 alone to configure, and maybe once this is configured and run, I should be able to probe the output of PWM 0. Okay, so again, so a structure and a new, the very first, and the new method is called disable, because when the PWM is enabled, configuring those registers or the values associated to the PWM might not be effective. That's why it's important to disable first and clear the scale. In the new method, everything is resetted and disabled. That's it. Okay, and return back all, initialize these counters to 0 so that there is no other default values in any of those registers. Then in the implementing these traits for PWM 0, so this is the structure here. It has pin, this should be the GPIO pin number and other hardware pin number, whatever you want, and the scale value, the prescaler value, and enabled or not. And it's, if you want, you can also add a frequency and a duty cycle, but let me, if there's a need, then I will add it. So on the prescaler, so how if you go through the FE310 manual, so in the configuration register, the last 4 bits scales the PWM counter before even feeding to the PWM comparator. Okay, so set scale, and it also says that the scale value x means that the division factor would be x plus 1. Okay, so first it clears the, I mean, in the pre-scale, first it clears the PWM scale value. Then it also checks if the scale value is less than or equal to 15 because it's only 4 bits. So it asserts that. Then it writes the scale value, whatever is passed to this function. Okay. Then the comparator value. Yeah. So this is the value to compare. For example, after how many clocks of the processor. So this is a running counter value inside the PWM, and when the PWM comparator, so for every input clock cycle, the comparator value would or the counter value will increment by 1, and this comparator value is the 1 for every time the counter changes. It would check against this value, and if it reaches this value, then it would raise the pin out. That means PWM out would go high. Okay, and that's this compare value after how many cycles you want this. That's why I said this is the one that would change the frequency of the PWM output. Okay, so if let's say that the input to the PWM is even before the prescaler it is 200 megahertz, and then after prescaler we divide that by 2, so 100 megahertz, and in the compare, if you set a value of let's say that 4 or not 10, then from 100 megahertz it will become 10 megahertz. Okay, and then after this one is like how many off cycles, so this would go high, and then how many cycles, this is a duty cycle. Okay, how many off cycles, so this you set it as in the PWM 0 there are 2 registers. One is comparator 0 and comparator 1. Actually each PWM in FE310 has 4 comparators, and each one helps you to fine-tune the frequency and duty cycle. Okay, and as usual, enable, here it is bit position number 1 to enable, and I think there is no in the PWM you don't have to wait for anything. Overview, so PWM count, configuration, yeah, you just enable, that's it. Enable always is 12, bit number 12, that's it. So that's enable, and if you invert and then that would be to disable. Okay, that's all. And now on the actual digital clock application, I would create these 2 high frequency crystal oscillator instance, and created with the method new, and I have enabled that, and I have configured the PLL to take this high frequency oscillators input and generate a clock of 200 megahertz. And maybe in the next lecture I would add code to invoke those PWM and test if this all the 3 works together or not. Okay, so that's the one which I will do in the next lecture. Okay, thank you.